Lesson P.1, Real Numbers. Most of what we discuss in this lesson is going to be a review of things we've talked about in previous algebra classes. At the end of the lesson, we'll discuss what's called Vedic math. It's a type of mathematics that is basically a shortcut, and we're going to use that to find the decimal value for a fraction. The complex number system accounts for every type of number we can work with. In this lesson, we're just going to focus on the real numbers. We're going to put the imaginary numbers on hold for now. So if we have our whole set of real numbers, we can break that down into subcategories. We can break real numbers down into rational numbers or irrational numbers. Irrational numbers are numbers like pi, radical 3. They have decimal values that never end or never repeat. Whereas a rational number, that can be written as a fraction. It has a decimal value that either terminates, it comes to an end, or it has a decimal that repeats. From there, we can break rational numbers down into another category, which are the integers, -7, -54, 23, 0. Those are all integers. Now we can break another subcategory from the integers into the whole numbers. The whole numbers include all non-negative integers. So we have 0, 1, 2, 3, 4, 5, 6, so on and so forth. And then last, we have the natural numbers, which, very similar to the whole numbers, the only thing are the natural numbers exclude 0. Often you'll hear natural numbers referred to as the counting numbers because we start with 1, 2, 3, 4, go on from there. That's your real number system. Next, we are going to discuss interval notation. First, we're going to refer to bounded intervals, which means we have two endpoints. All right, so let A and B be real numbers with A less than B, and then A and B are the endpoints of each interval. So there's 4 different cases we can have. We have our interval notation compared to our inequality notation. This is the notation we first learned back in middle school, and now we can learn interval notation. This is what we use most often in pre-calculus and calculus classes, higher level mathematics. Okay, it's just an easier notation to work with. So if we have our 2 endpoints and they're closed, closed means those endpoints are included. So we have our brackets rather than parentheses, which if we look at the graph, our endpoints are filled in circles. If we have an open interval, which means the endpoints are not included, we use parentheses around A and B, and we can see our endpoints on the graph are open circles because those endpoints are not included. And the last 2 we have half open because one endpoint is included, the other is not. So you can see how the interval notation relates to the inequality notation and then how that relates to the graph. Now we are going to discuss unbounded intervals, meaning we have one endpoint, but we're extending in one direction that's not coming to an end, so we have infinity involved. In this one, when we're talking about the interval type, can be a little confusing, all right? Because when we have infinity, that's an idea, it's not a number, it's a concept. This will never be a closed bracket if we have infinity, an unbounded interval there, all right? So even though we have a parenthesis here, this is a closed interval because the one endpoint we do have is included, which we can see on the graph. The next one's open because the one endpoint we do have is not included in an open circle. And then you can see the last 2 very similar, except we're approaching negative infinity as we go to the left. On the right side, we have our endpoint that's included. So again, this is a closed interval, which we can see is a filled in circle on the graph. Then the last one, only difference being that open endpoint. Now we're going to discuss a few properties that you learned back in middle school: the commutative, associative, identity, inverse, and distributive. These relate to addition and multiplication. So commutative is basically saying the order in which we add or multiply two real numbers does not matter. Our result is still going to be the same. The associative property, if we have three real numbers, it does not matter whether we add the first two numbers together first or if we add the last two numbers together first, our result will still be the same. The same works for multiplication. The identity for addition is 0. If we take a real number and add 0 to it, we're still going to have that real number. The identity for multiplication is 1. If we have a real number, we multiply it by 1, we still have that real number as a result. Next, we have the inverse property. If we have a real number and we negate that, make it the opposite sign, if we add those two values together, we get 0 as a result. The inverse for multiplication is going to be the reciprocal of the number. So if we have a, we have to multiply it by 1 over a to get a value of 1. So for example, if we had 7, we would multiply that by 1/7 to get a value of 1. Those are the inverse properties. The last one, distributive. If we have a number multiplied outside of a sum inside the parentheses, we have to distribute that value to each of those values inside the parentheses. So we have to take a times b plus a times c. The last thing before we get to Vedic math is a review of properties of exponents. Okay, so suppose m and n are positive integers and a and b are real numbers, then the following properties are going to be true. First, we have the property of 1. If we raise any real number to the first power, we're still going to have an answer of that first number. Any number raised to the first power is itself. Property of 0, any real number raised to the 0 power is equal to 1. Property of negatives, we always want to work with positive exponents, so this allows us to create that positive exponent. If we have b raised to the negative n, we have to take the reciprocal of that, so we write that as 1 over b to the positive n power. The product power, if we have the same base a and we're multiplying those two real numbers together, we add our exponents. We would take a raised to the m plus n power. The power of a power property, we have an exponent raised to an exponent. We multiply those two exponents together. Power of a quotient, if we have a fraction inside the parentheses raised to an exponent, we have to distribute that exponent to the numerator and the denominator. Power of a product, if we have two factors being multiplied inside the parentheses raised to a power, that exponent has to get applied to the a and to the b. It has to get applied to both factors. And then the last one, the quotient property, if we have the same base a raised to the m and the n power, then we simply have to subtract those two exponents. Something I want you to do for class, because we've talked about it in the past, how can we use the quotient property to show why the property of 0 is true? How can we use the quotient property to say why any real number raised to the 0 power is going to be equal to 1? Okay, so this is a type of proof. I want you to go through and show why this property is true. Have that ready so we can discuss that in class. You might not come up with the answer, but I want you to at least think about that process. I'm going to show you how we can use Vedic math in order to find the decimal value for any fraction. Okay, in particular, we're going to discuss fractions where in the denominator we have a 9 and some place value out in front. In this case, we're going to take 1/19. Okay, we could use this for 1/29 as well, and so on. First thing we have to do, we're looking at this 1 in front of the 9. We take that and add a value of 1 to it. So 1 plus 1 gives us 2. That becomes our multiplier. Now what I need to do, I'm looking at this 1 in the numerator. I start with 1, and I'm going to multiply that by 2 each time. Okay, so I'm going to move this over. We have that value of 1. If I multiply that by 2, I get 2. Now I'm going to multiply the 2 by our multiplier. So 2 times 2 gives us 4. 4 times 2 gives us 8. 8 times 2 gives us 16, I carry that 1. 6 times 2 gives us 12, plus 1 is 13, carry the 1. 3 times 2 is 6, plus 1 is 7. 7 times 2 is 14, and I carry that 1. 4 times 2 is 8, carry that 1, gives us 9. Looking at this, I could continue this pattern on, but one thing about fractions and the decimal approximations, or the decimals value for those fractions, if I look at the denominator, I have 19. We know this fraction is going to terminate, come to an end, or it's going to repeat, and there's a rule that tells us it has to repeat by, if I take the denominator, which is 19, if I subtract 1 from that, that gives us 18. This decimal has to repeat by at least 18 digits. So far we have 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. 9 is half of 18. So part of this Vedic math, I can take the complement of each of these numbers. Meaning, I'm going to look at my 9. The complement of 9 is the number that I add to that to get a value of 9. The complement of 9 is 0. If I look at 4, what number do I have to add to 4 to get to 9? That's 5, 2, 6, 3, 1, 5, 7, and 8. So now I'm going to combine both of these rows, which is going to get us 0, 5, 2, 6, 3, 1, 5, 7, 8, 9, 4, 7, 3, 6, 8, 4, 2, 1. And that is the decimal value for 1/19. This is going to be the part that repeats. Okay. If you type this in on your calculator, you're not going to get this because your calculator can only show so many place values. You would have to go on the internet, Google a large decimal place calculator, and you would come up with this value. So this is how we can use Vedic math. It involves lots of tricks and shortcuts for certain parts of mathematics.